Everyone thought it was pilot error. They were profoundly wrong. In the late 1950s, the Lockheed L-188 Electra was hailed as the future of air travel. A sleek, fast turboprop, it promised jet-like speeds with propeller efficiency. Airlines clamored for it, passengers loved its comfort. But within a year of its debut, the Electra became synonymous with a terrifying, inexplicable phenomenon: aircraft disintegrating midair. December 1958. Braniff Flight 542, an Electra, departed Houston, Texas. High above Buffalo, Texas, disaster struck. Without warning, the aircraft broke apart at 15,000 feet, scattering debris across miles of farmland. All 34 people aboard perished. Investigators found no evidence of fire, explosion, or structural fatigue. The cause was a mystery. Then, less than 3 months later, in March 1959, American Airlines Flight 320 suffered a similar fate. En route from Chicago to New York, the aircraft crashed into the East River during its approach to LaGuardia. Although this was attributed to pilot error, the chilling similarity to the Braniff crash was not lost on the aviation community. The real alarm bells rang a year later, March 1960. Northwest Airlines Flight 710, another Electra, was flying from Minneapolis to Miami. Over Cannelton, Indiana, at 18,000 feet, the Electra disintegrated, mirroring the Braniff crash almost exactly. Again, no warning, no distress call. All 63 passengers and crew died. 3 catastrophic in-flight breakups within 15 months, each involving the Lockheed Electra. The public was terrified. Was this a new, undetectable form of sabotage, or a fundamental, fatal flaw in this revolutionary aircraft? The Federal Aviation Agency, then called the FAA, was under immense pressure. They issued emergency speed restrictions on all Electras, limiting them to 225 knots, far below their advertised performance. Airlines were facing cancellations and public outcry. Lockheed's reputation, and indeed the future of turboprop aircraft, hung in the balance. The investigation was unprecedented. The full resources of the FAA, NASA, and Lockheed's own engineers were brought to bear. They meticulously reassembled wreckage, poring over every fractured rivet, every twisted piece of metal. But the evidence was bafflingly inconsistent. No common point of failure emerged. One theory gaining traction was flutter. Flutter is an aeroelastic phenomenon where aerodynamic forces and structural elasticity interact, causing violent, self-sustaining oscillations that can tear an aircraft apart. But the Electra had undergone rigorous flutter testing. It was considered virtually immune. The key to unlocking the mystery lay in a small, seemingly innocuous detail from the Braniff crash. Recovered from the wreckage were sections of the left wing. On one piece, investigators noticed an unusual pattern of stress fractures, radiating from the engine nacelle. This led to a groundbreaking, if initially controversial, hypothesis: propeller whirl mode flutter. It was a complex interaction, far beyond simple wing flutter. The Electra's massive turboprop engines, mounted on long, relatively flexible wings, were the culprits. Here's how it worked. If an engine mount or gearbox failed, even partially, the propeller could begin to gyrate slightly. This subtle gyration, at certain airspeeds and altitudes, could induce powerful, resonant vibrations in the entire wing structure. Think of it like a washing machine load becoming unbalanced. These vibrations would rapidly escalate, feeding back into themselves. The wing would twist, turn, and flex with increasing violence until the forces simply overwhelmed the aircraft's structural integrity. The wing would detach, followed quickly by the rest of the airframe. The theory was elegant but required proof. Lockheed engineers, working with NASA, built a sophisticated mathematical model of the Electra's wing and engine dynamics. They simulated various failure scenarios. The results were chillingly consistent with the crash evidence. The breakthrough was publicly announced by the FAA in May 1960. The design flaw wasn't an inherent weakness, but a previously unknown aeroelastic phenomenon that could only manifest under specific, rare conditions of engine failure and flight parameters. It was a perfect storm of physics. Lockheed immediately launched an ambitious and incredibly expensive modification program known as the Lockheed Speed-Up Fix. Every Electra had to be grounded and modified. This involved strengthening the engine nacelles, stiffening the wing structure, and reinforcing various airframe components. The modifications cost Lockheed millions of dollars and took months to implement across the entire fleet. The public's confidence in the Electra was severely shaken. Many airlines canceled orders or sought to replace their Electras with jets. Despite the initial setbacks, the speed-up fix worked. Once modified, the Lockheed Electra became one of the safest aircraft in the sky. No further in-flight breakups due to whirl mode flutter ever occurred. The Electra's story isn't just a tale of disaster, but of remarkable engineering triumph. It forced the aviation industry to confront an entirely new aeroelastic challenge. The lessons learned fundamentally reshaped aircraft design and testing protocols for decades to come. It demonstrated the immense complexity of aerodynamic forces at play, especially with new technologies like powerful turboprop engines. The crashes served as a stark reminder that even the most rigorous testing might not uncover every potential flaw until an aircraft is put into real-world service. The Electra continued to fly for decades, primarily in cargo roles and with some smaller airlines. Its distinctive, deep hum became a familiar sound at airports worldwide. It served with distinction, a testament to the fact that even a flawed design can be made safe through dedicated engineering. The Electra flap was a pivotal moment. It highlighted the critical importance of investigating every piece of wreckage, no matter how small, and the willingness to challenge preconceived notions about aircraft safety. It ensured that future generations of aircraft would be built with an even deeper understanding of the forces they faced. The legacy of the Electra's early tragedies ultimately made the skies safer for everyone. From the ashes of those mysterious crashes rose a new era of understanding in aerospace engineering. Discover how another engineering marvel, the Comet, faced its own catastrophic design challenges in our next deep dive.